Alright.
Okay, we're starting. We're going to finish our marginal function.
My test is actually more than hard. My counting. My stats test.
Move on to exponential growth and decay. I didn't bring any extra handouts, but if you don't have the handouts, they're online. You can look them up on your cell phones. So on our class webpage, you can scroll down to the bottom. There's a section called Documents. You can pull it up there on your phones. So I forgot what section this was, but it's marginal function. So I believe we did part A and B of example 2, but we'll just redo it just to sort of jog your memories. And so this is from the handout. We're given a demand function of this. Remember, P here represents the price we can sell for. Right, so that was how much the price that customers are willing to pay for X items in the market. Okay, so we can that. So that's what we're given. That was our demand function. And in part A, we wanted to find the marginal revenue. So what do we know about revenue? How would I describe the revenue from selling X items? Yeah?
Price times quantity.
It's price times the quantity, right? So it's the price times number of items sold. That's the basic idea. Basically, also, we were given the price based on this function, so that's really P times X, which is the number of items. I'm talking about the revenue X. Right, so this you can sort of think of as a general formula. This will always be true. So that's a general formula that you can know. So the revenue is the number of items I'm selling times the price of each item. That is the total amount of money I can bring in from selling X items. So here, we ended up with our revenue function was this guy, 25 over radical X times X, which I could simplify to 25 radical X by simplifying. So that was our revenue function. So what is the marginal revenue? How did we find the marginal function? Yeah?
Derivative.
It's just derivative, right? So marginal was another name for the derivative, and that basically that word comes from the interpretation that we're putting on the derivative in this context, which we'll talk about pretty soon. So our prime of X is going to be the marginal function, which is going to be 25 over 2x. So this is called the marginal. And that's basically it. Finding the marginal function is finding the derivative. Okay. So it's just another name for derivative. What is the marginal revenue when X equals 100? So this is pretty much our prime at 100. It's 25 over 2 times radical 100. So we just plug it into our marginal revenue function. So that gave us 25 over 20, which was 1.25. So it says find that number and interpret that number based on what we know about marginal functions. How would you interpret that number? Yep.
When you produce like one more of the thing, you make $1.25 more.
Okay, so the marginal function at a certain point tells you the change, the additional change you will incur by going one more step, right? That's kind of our interpretation. So here it's basically saying 125 is the additional revenue to be gained by selling one more item. Right? And this is, again, remember the revenue was an approximation. It's like we're using a tangent line approximation to approximate the revenue. And so this is additional revenue i.e. the additional revenue from selling the 101st item. And that's sort of where we left off last time. So the marginal function is just a function that tells you if you produce one more, what is going to be that additional change. Okay, and it applies to any function, so you can talk about marginal cost. It's what's the additional cost of producing one more item. Marginal revenue is what the additional revenue will be gained by producing one more item. Marginal profit, what is the additional profit we will gain by producing one more item. It's the guy that tells you one more, what's happening at your margin. So now we move on to C. And the definitions of the function is also important for you to know, so you need to know how to find revenue. The cost function is always going to be given to you. It's not really something you can deduce on paper. It comes from you just paying attention to what's going on, finding statistics, doing research, and things of that sort. So the cost function, there's no general formula for that. It really depends on the situation. But the revenue function is pretty much always, you're figuring out, if I sell this many things at this price, how much money I make. That's always going to be true. Right. So in C, we're given a cost function. This is the cost to produce X items. And we want now the marginal profit. So marginal profit just means derivative of the profit. So the first thing we need to figure out is how do we find profit. And so if P of X is my profit function, how do you find profit? Yeah?
Revenue minus cost.
It's revenue minus cost. So it's the amount of money you basically take home. So if you get all the money that comes into your business and you subtract all the money that goes out of your business, the things you have to spend on labor, on rent, on producing things, that the profit is what you have left over. So this is going to be revenue. Let's write it out. Revenue minus cost. So in other words, P of X as a general idea is going to be R of X minus C of X. You can flesh that out a little bit more by plugging in the revenue formula. Or you can say that P of X is going to be X times P minus the cost function. So this is the number of items sold. Price per item and this is the cost. So that's how we find our profit function. So here, what's the profit function?
$25 X.
25 root x, was that the revenue?
Yeah.
I erased it. Okay. And the cost function is going to be the guy that's given. Like I said, cost, no general formula for that. That's always has to be given to you or indicated somehow how to find it. So I'm going to subtract x squared plus 2x. So in other words, here my p is equal to 25 radical x minus x squared minus 2x. But we're after marginal profit. So we need to find the derivative of this guy, which is going to be what? Well, this guy we already found the derivative for. That's 25 over 2 radical x minus derivative of x squared.
2x.
Derivative of 2x.
2.
So we still remember how to do the power rule. Just checking.
I look, you forgot that coming back.
So that is what we were asked for. What is the marginal profit function? So that is the general function for marginal profit. So that was part C. In part D, want the marginal profit when x equals 100. And again, that's just you plugging in. So this guy, I believe we already computed, was 1.25. It's 200 minus 2. So what is that going to be?
Negative 200.75.
Interpretation. How do you interpret that number? Yeah?
Does that mean with the 101st thing you sell, you lose $200?
You lose $200. The idea of the negative, what that means is you would lose pretty much two. If we're I didn't really mention what units we're doing, but let's say we're using dollars. You would lose $200 by producing, or more specifically by selling. So once you produce it and sell it, you will get a loss by selling the 101st item. Right, so you go one more, you're losing $200. Which leads us to the following question, which is should be a no-brainer at this point. Is it worth producing one more? Well, if your goal is to make money, the obvious answer is no. You would lose money. In fact, the fact that our profit is minus 200 probably means we shouldn't have been producing for a while. That's we're in the hole by a lot there, relatively speaking. And it's one of the reasons, you can see one reason why is because our cost function was actually a quadratic. That means our costs kept increasing, and it turns out that it outdid our revenue, right? Our revenue was a radical, right, which increases very slowly. Radicals just increase like that, whereas a quadratic is going to increase like that. There will be a point, if that was your cost structure and that stayed the same, and your revenue stayed the same, there had to be a point where you ended up in trouble. And based on that number, that point kind of happened a while ago. So this is sort of one of the reasons why marginal functions are studied. They can kind of tell you about what's going to kind of happen in the future, assuming that conditions are the same as they are now. And you can keep track of what you should be doing, what your next steps should be by paying attention to the marginal functions. Right? So if you kind of historically plot data about your costs, your revenue, and all of that stuff, and you sort of somehow extrapolated from that how to find tangent lines and develop sort of functions that talk about the derivatives of these functions, you can kind of look at those functions and kind of tell, okay, this will be going too far. We need to stop here and do something. And so that's basically it. So problems like these, and you can see these from the review as well, I'm pretty much always going to sort of ask you about these, so I just want you guys to know about the ideas behind what is revenue, what is profit, what is cost, how do these things affect business decisions, how these things, what the marginal function would mean, that sort of thing. So the problems like on a test or anything like that would be very similar to this. Are there any questions? So the thing is, the hard part of the class, I think, for the most part, is over. Right? There's nothing that's going to be too complicated. Now, right now, we're kind of just applying concepts that we learned before. So here we're using the derivatives to talk about other things, and we'll be stuck in that mode for a while. There's going to be another slight bump in the learning curve when we talk about integrals, antiderivatives, but for the most, that's not going to be so bad because we're not doing a lot there. But yeah, after taking all that time and all that work to develop the theory behind what a derivative is, applying them isn't so bad. Once you really understand what a derivative means and how it can be interpreted, it's not so bad. If there are no questions, we'll move on. So we can have a shot at those bonus problems. So like I said, all these handouts, they are online, so you can pull them up on your phone. So for these sets of equations here, so we're moving on to the next topic, exponential growth and decay. Where did I stop? Did I hand out the related rates handout to you guys or no?
Yeah.
I did, okay. We won't get to that today, but bring it for next class tomorrow. And as I said, a couple of people had problems with the test being on Tuesday, so I would think Friday is going to be the day. But I need to make sure to square that away with my other classes first. So by end of day, I'll know and I'll let you guys know. To make sure my life isn't in danger. I hope you're not even thinking about it, Joel. Okay, I'm not considering it anymore. I'm sorry. Go back to the original thing. Okay, so exponential growth and decay. A very important application. Usually it's applied in science. Not so much business, but the ideas are still sort of useful too. For the most part, deriving these formulas would require us knowing antiderivatives, so I'm not really going to derive anything for you. So at this point, you can take these formulas on faith at the moment. And towards the end of the semester, if anyone's interested, we can go back and derive where these guys came from. The first, equation 1, though, is pretty much the definition of what it means to grow or decay exponentially. So that first equation in each of those boxes is pretty much the definition. We say we have exponential growth or decay if a quantity grows or decays proportional size. This happens when it grows by a fixed relative amount. Right. So we can contrast this with linear growth, which we've also talked about since lecture 1. And we said something grew linearly if there was always a fixed absolute amount that it was growing by per unit time. So we did that example when we were talking about renting a car, and I said for each additional mile you drive, it's $2 extra. It's always going to be $2 no matter what. Every time you add a mile, you add $2 to the bill. Add another mile, add $2 to the bill. You're adding a fixed amount. When you have exponential growth, that's not how it works. You add a fixed percentage amount. So you add a certain percentage of what the current amount is. And so the value of what you're adding actually changes over time. It tends to increase in the case of growth or decrease in the case of decay, but it grows by a proportion of the current size. So there are many things that exhibit this kind of growth. Populations are one of them, for example. Right? So if you have a population of 10 people, it's not going to grow as fast as if you have a population of 100 people. You have a lot more people making babies, right? So the actual specific number of babies that are made will be larger the larger the population grows, right? So it's not a fixed amount of things being added, right? But the larger the thing is, the more it grows by. And when it gets bigger, it even grows by even more. Things that exhibit this kind of behavior, we say they vary exponentially. So you can have a population where you're like 20% of the population is having babies and blah, 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 and you can minus the death rate. But that 20% changes over time, right? As the population grows, that 20% represents a larger number of people. And so there are many things that exhibit this kind of growth. There are more things that exhibit exponential growth than linear growth, because usually if you have more of something, the more it's going to produce. And that's a very typical situation to deal with. And decay is also the same. There are many things that have exponential decay. I guess the most striking example would be in science when you're looking at sort of like atoms decaying into lower atoms or radioactive elements decaying. But yeah, so that's kind of the basic gist of it. So when you talk about the definition, so if P is the amount then you can say that the rate of change of P, how fast P is changing, is going to be some constant amount times the current amount. That's what it means to be proportional. Right? So here, this guy is a constant. It's called, and this is important because the names can be confusing. So this is called the relative growth rate. Or it's sometimes called the growth constant. And that's just what proportion is being added. Right? And P, of course, is from the original function. This is the current amount. So any quantity that you see behaves like this, where its rate of change is just a constant of its current amount, you say you undergo exponential growth. So you can say something is always increasing by 2% of its current size, or something is always increasing by, or it's decreasing by 2% of its current size. Right. Whenever something like that happens, you have exponential growth. And so it turns out this is something that's called a differential equation. Now there are entire classes about things like this because it's a very, very important thing. Many things can be described by differential equations in physics and engineering, in life, right? Basically, though, the concept itself is not that complicated. A differential equation is just an equation that has a derivative in it. You call it a differential equation because there are derivatives in the equation. But yeah, so this is called a differential equation. So if I ever ask you for a differential equation and we're in exponential growth, this is the guy I'm asking you for. And it turns out we can solve this using something that we don't know how to do yet. So just take my word for it. We can solve this for p. To solve a differential equation means you want to get rid of the derivative. You want to find a function that satisfies the equation where derivatives aren't present, and you end up with this guy, which I refer to as the PERT formula. It's a way to remember it. PERT like the shampoo. I don't know if you guys remember that. Guys are babies. When I was young, they came out with a shampoo called PERT. It was like the first ever shampoo to be shampoo and conditioner in one. It's like groundbreaking. It was like, oh my god, the technology! You know, that's the kind of things that we got excited about back in the 90s. Like, I'm gonna save so much time. I don't have to wash my hair only once. Okay, so PERT. They're P-E to the RT. E is the same guy that we've had before. It's the exponential Euler's number, the 2.71. We've dealt with exponential functions before. R is going to be the growth constant. So that's going to be telling you your percentage amount that you're growing by, usually written as a decimal. T is time. P naught is the initial amount. So this is just a notation for how much did you start with, right? And then this is going to be the current amount. So anything that exhibits this growth, you can actually track how much of the quantity there is using this formula. Right? And so that's sort of the important thing. There's also an equation that can accompany this, where someone can tell you, at time equals 0, the amount is P naught. And this is just notation for whatever the current amount is. Right? And this guy here, this equation is called the initial condition. So a lot of this topic is just going to come down to you knowing these equations and knowing the names of each of these equations, because the problem is going to ask you to find them. Is there anything else I want to mention here? Maybe talk a little bit about doubling time. Basically, this is the time to double. And the formula for that is ln2 over r. So let's actually, so it's a good like mini review of derivatives as well, a little bit. So let's actually figure that out. So let's say I know that p is equal to p naught the RT. Right? So P naught is how much I start with. Right? So if I want to find out the time to double, how would I use this equation to figure that out? Ideas on what we can, yeah?
Set P on the left side to 2P. Like,
Yeah, to 2P naught, right. So if I start with P naught, what we need to do is figure out at what time is the current amount equal to double the original amount. So what you would do is you plug in 2P naught on this side equals P naught on that side. Yeah, Jacob is on point. He was studying. I thought he was joking. I believe him now. It's like, he's been answering questions all day. He's like, oh yeah, it's yeah. He's gonna go home and collapse.
I used all my brain power for that problem.
That was the last. Right, so that's how you can do it. Now, so this is some non-zero amount. It's going to be amount of something we're measuring, so we can divide both sides by that, and so we end up with 2e to the RT. How do I actually solve for t? I care about the time to double, which means I need to solve for t. In that equation, how would we solve for t? Yeah?
Put both sides ln.
You can ln both sides, right? So remember, one of the reasons how we use logs and exponentials is if you have an exponential, you want to get rid of it, use a log, right? So we use log to the base e, which is ln. So I would ln both sides. And then what would happen? Yeah?
ln cancels.
Right, ln of e to anything is just the thing, so this, not technically correct to say it, but you can kind of think of it that way. Once the ln and the e are beside each other, they cancel. So I have ln2 is equal to r times t, and so this would mean that t is equal to ln2 over r. And so that's where that last equation in the box came from. Okay. But at this point, you can just have that memorized. The time to double is going to be this. So if I tell you something is growing exponentially, this is the percentage by which it's growing, how long before it doubles in size, that would be the answer. Or you take ln2 divided by the percentage. And by the way, there's nothing special about this 2, for example. I plugged in 2 because that was the time to double, but if I wanted the time to triple, I would have put a 3 here, and I would have ln3 over r. The time to quadruple is ln4 over r, etc. So figuring out how you can, looking at orders of magnitudes for exponential growth functions, it's pretty easy as well. The time to have n times the size you started with is ln of the n over r. So that's all it's going to be. The difference between exponential growth and decay aren't that many. Basically, if you put a negative sign in front of this, you get decay, because we remember, hopefully we remember, if we have e to a positive power, it looks like this. If the power is greater than 1, so this would be like e to the x, whereas e to the minus x would decrease. Right? So the idea is if you want to grow, use this equation. If you want to decrease, just put a negative on the power, and all the things kind of work out very nicely. So that's just a slight discussion of these forms that you have on the first page. Let's actually see if we can get through an example. So it's important that you know these formulas and know like what we call them, because usually in these problems, exponential growth and decay, they will be word problems. They'll be very similar to this, and each one is going to ask you for a specific thing. You need to be aware of what you're being asked for, and so you will know which one of these formulas you want to employ. Okay, so let's actually just jump into the examples. You can probably get through one of them, and we'll do the 2 others tomorrow, as well as jump into related rates. Example 1. P is the current size of a population of bacteria At 10 a.m. there are 50 bacteria, at 3 p.m. there are 350. Assume the rate of growth of the population is proportional to its current size. Right? So the first thing, if we're doing example 1, that phrase, proportional, to its current size, that is an indication that you're doing exponential growth, right? That by definition. Right, so here in the question it never mentions that we're doing exponential growth, but that phrasing tells you it's exponential growth. So that's what tells you, you know you're not going to use a straight line to talk about this problem, you're going to use an exponential function to talk about this problem, and then all these formulas actually apply. Right, so it's important that you read the question well, how it's starting off, right, because on the next test this won't be an issue, but on the final where I'm testing on everything, you need to know when you should be using linear function versus another kind of function. And this kind of sentence is one way in which I'll let you know the difference. So either I'll specifically tell you, think of it as an exponentially growing thing, or I can say something like it's proportional, it's growing proportional to its current size. That should hint to you that this is what you want to use. Okay. So we're given the size of the population at 2 points in time, and now in A we want to find the relative growth rate. Now, if I ask for the relative growth rate, what am I asking for? Which one of these symbols on the other page?
Is it R?
It's the R, it's the little r. Right? So when the question asks for relative growth rate, they're asking, what is the little r? Okay, so now I know that we are after the little r. How do we find it? What equations can I use? Well, I can use one of the formulas that has the little r in it. So we can use the PERT formula. Okay, and how do I apply that formula? Right, so I'm after this little r right here. Yeah?
You would set like 350 equals 50 ER 5, because it's like 5 hours.
Okay.
And it's all
So
metric.
here you're saying t is time in hours. Okay, that's cool. And you know that P naught is equal to 50 because they told you in the beginning we had 50, right? So there was a point in time. So I'm taking t equals 0 to be 10 a.m. and this is P of 0. Okay, so that's what we started with. And I also know that when t equals 3 p.m., which is when t equals what? That would be 5. Right? I know that p is 350. So from the original sentence that's setting up the problem, we know we should be using exponential growth. And so now we want to glean all the information from that problem that we can get. We know that we started out with 50, so that's actually telling me P naught. I set that to be time equals 0, 10 a.m. So at 3 p.m., that's 5 hours later. So when my t equals 5, I know that the current size is 350. So now I can just go and plug into the PERT formula because I know literally everything except the guy that I want, right? I know what the current amount is, 350. I know what the initial amount is, 50. I know what the time is, 5. And so that's my only unknown. And so now I just want to solve for R. How do I solve for R?
Move 50 to the other side.
Okay, so first you want to divide both sides by 50. And so that would be what, 7?
Yeah.
Now what?
I'll on both sides.
Off both sides. So here I get 5R is equal to ln of 7. means R is going to be ln of 7 over 5. So in B, I want to find a formula for P of T. The general formula, how can we say it? Write it down now.
So it's P equals 50 P to the ln 7 divided by 5 times 5.
So when you're writing down a general formula for something, in this case, remember your T and your P, those are the variables. The T is going to be like your input, the P is going to be your output. So if they're asking you for a general formula, the guys you need to fill in is the P naught and the R. Those guys are always going to be constants, and those guys are ones you should be able to find based on the information, right? So the P naught and the R, these are going to be the constants. P naught is the amount you start with. R is the percentage growth rate as a constant. And so that's our general formula. There's nothing else to do. Basically. What is the size of the population at 4 p.m.? So what are we looking for here?
P.
The P. So what is P at T equals 4 p.m. would be what? 6. So that's 6 hours after we started. Right? So that kind of, you knowing that that's what you're looking for kind of comes from interpreting the problem. We know that 10 a.m. is time equals 0. We're measuring time in hours. So at 4 p.m. is 6 hours from the time we started. And so basically here what we want is the population when time equals 6. And so I'm just going to use this formula because I just wrote that down. So that's 50 e to the ln of 7 over 5 times 6. And that's the answer. The hardest part is figuring out what you should be looking for. I mean, once you've done that. The most complicated thing is going to be you solving an exponential equation, which hopefully by now we all sort of know how to do that. Rate of growth at 4 p.m. Okay. Now, one thing I want you to remember is that rate of growth is not the same as the relative growth rate. This is kind of why I want you to pay attention to the wordings of this. Right? Rate of growth here refers to the rate at which t is changing. This is p prime. So this question is asking about p prime. Right? So they have to either use the word relative or it has to say something like growth constant. Right? But if it says rate of growth, or what is the rate of change? Rate of growth or rate of change is referring to the derivatives. So they can both have growth in the title, but the important thing is knowing whether it's relative growth or overall growth. That's the difference. And again, this comes from a straightforward formula. This is P prime equals RP. So this means my rate of growth, the R I know, that's ln of 7 over 5. And P, I want it at 4 p.m., so this is pretty much when t equals 6. So it's going to be, this is the size. Right? So it's going to be the current size times that. And that's your answer. Let's finish off this here. When will the population be 1,500? How do we figure that out? Yep.
Have P equal 1500.
Plug in P equals 1500. I know we started with 50. ln of 7 over 5t. I'm looking for when, which means I'm looking for time. So I divide both sides by 50. What does this become?
30.
Huh?
30.
Huh?
30.
30 equals e to the ln of 7 over 5t. Of course, here we know we can ln both sides to get rid of that. ln of 30 is equal to ln of 7 over 5t, which means my t value is going to be ln of 30 divided by ln of 7 over 5. Or I can write that as 5 ln of 30 divided by ln of 7. It's okay to leave your answers. Definitely what you shouldn't be doing is like multiplying a 5 into the ln. You know, once things are inside the ln, you can't mess with them. So don't cancel things from inside the ln or anything like that. That would be We'll do the other two problems tomorrow, as well as move on to related rates. So bring the handout for related rates. And we'll stop there.
You want 3.2?